Welcome back to the Explainer. Today, we're kicking off part one of our deep dive into power flow, or load flow, analysis. And I want to start with a pretty wild thought. Imagine a massive network of generators, loads, and transmission lines stretching across entire continents. How do grid operators know exactly what is happening at every single point of that system at any given second? Well, they use the single most run study in the entire power industry, power flow analysis.
Okay, let's dive into this. Picture a huge power grid, and on this grid there are thousands of connected locations, flashing with unknown values. Just question marks everywhere. Unknown voltage magnitudes, unknown angles. You need to know what is the actual voltage and power flow at every single point, right now. It's a massive, chaotic, and highly complex problem. And get this, power flow analysis is run thousands of times a day across every grid on Earth just to figure that out.
Now, power engineers represent these interconnected grid locations using a standard network diagram, and they refer to these connection points as buses. But remember, real power grids don't just have 4 or 5 of these buses. We're talking tens of thousands of them, all interconnected by transmission lines. You have to run this analysis constantly to figure out exactly what is happening at every single node just to keep the lights on and the whole system perfectly stable. So how in the world do we handle all that complexity? Well, the whole chaotic network diagram elegantly collapses into this one mathematical object, the bus admittance matrix. Most people just call it the Ybus. It's brilliant in its simplicity. Each diagonal entry is simply the sum of all admittances connected to that specific bus. And every off-diagonal entry, that's just the negative admittance directly between two buses. Boom. It perfectly and systematically maps out every single connection in the grid.
Now, what's really interesting about this is a very specific number, 80 to 90%. See, because each bus typically only connects to a handful of neighbors, maybe 2 or 3 lines out of a massive system of thousands, the vast majority of the entries in our Ybus matrix are just zeros. This massive sparsity of 80 to 90% zeros is the actual magic trick. It's what makes solving networks with tens of thousands of buses computationally realistic on a computer instead of, totally impossible. All right, let's look at classifying the grid's players. We have our map with the sparse Ybus, but now we need to categorize the players on the board to organize our knowns and unknowns.
Every single bus has to be strictly classified into one of 3 types, and this is basically your master key for organizing the math. First, think of the red category, the swing or slack bus. This is usually your largest generator, and it sets our system reference. Here, we know the voltage, magnitude, and angle, while the real and reactive power are unknown. Second, in blue, are the PV buses. These are our generators with controlled voltage. For these, we fix the real power and the voltage magnitude, and we have to solve for the reactive power and angle. Finally, in green, we have the PQ buses, which are our loads. These make up about 80% of the entire grid. Here, we specify the real and reactive power demand, and solve for the voltage magnitude and angle. Those are the 2 big unknowns at every load point. Let's pause for a quick check here, just to make sure we're on the same page. Why does a power flow study need exactly 1 swing bus? Think about it for a second. You can never have 0, and you can absolutely never have 2. Why exactly 1?
So the crucial point is this classic chicken and egg paradox. In any power system, your total generation must exactly equal your total load plus the system losses. But here's the catch. You can't possibly know what the system losses are until the power flow equations are actually solved. It's a loop. So the single swing bus acts as the perfect slack machine. It automatically absorbs whatever unknown power mismatch is left over. If you had 0 swing buses, the equations literally couldn't balance. If you had 2, well, the problem would be overdefined with no consistent solution at all.
And this brilliantly illustrates how we've taken a massive, chaotic diagram full of flashing unknowns and systematically organized it into a highly manageable mathematical model. The physical network collapses into a sparse Ybus matrix. Every single bus is strictly classified as swing, PV, or PQ. And we're left with exactly 2 knowns and 2 unknowns per bus. The mathematical board is now completely set.
Let's move forward and see how this builds into our next step. Our knowns and unknowns are perfectly set up, but having the board set isn't the same as actually winning the game, right? How do we crunch these massive, nonlinear equations to iterate our way step by step to the true solution? In part 2 of this explainer, we are going to tackle the heavy-hitting algorithms that do exactly that: Gauss-Seidel, Newton-Raphson, and fast-decoupled. Until then, I'll leave you with this to think about. If an entire continent's power grid relies on guessing and iterating these equations thousands of times a day, what happens when the math completely fails to converge?